I'm Jen Gartz. I'm from TechSoft 3D, and I'll be your MC/cruise director for the day. Joining us from the TechSoft side, we've got David Grieve. He heads up partner development here at TechSoft, and Andreas Rodriguez Villa. He's our product manager for our CAE products. And then we're stoked to have a couple guests. We've got John Wild. The VP of Product Management at SimScale, and then we've got Andrew Sortorelli, Product Manager at Synera. So thanks everybody for joining us. And all right, looks like we've got a pretty good group. So I'll let you take it away, David.
Thanks, Jen. Hey, I'm thrilled to be here. This is actually our first CAE Summit. It's a brand new product range for us. We acquired 2 companies during the COVID period, and we've now launched these out. So I'm thrilled to be part of this first monumental, I meant to say, occasion. So thanks, Jen, for the introductions. I just want to quickly run through the agenda today. I'm going to give you a quick overview of TechSoft 3D, our company, and explain a bit about us, about how we work. Andreas is going to give us a simulation analysis workflow and run through that, and then do a demo. And then we have 2 partners and users of our technology that are going to give you a showcase of how they use it within their engineering software and how they make use of our tools within their software. And then there's going to be questions and answers. You feel free to add them into chat along the way. That's the best way to do that. We'll be monitoring chat. So if you've got anything that comes up, stick it in the chat box. You'll find that down on the bottom toolbar in Zoom. So I just want to explain a little bit about TechSoft 3D. We're an SDK company. We make component software. We don't make end user products, but what we're doing is making the bits and pieces, the components that you need to create truly great engineering software. We've been going around for 26 years now, and we have over 650 partners worldwide using our technology to create their applications. We spread the world with people in every continent. We're very engineer heavy. We have a big team in Lyon in France, which we've been growing out as we've grown the number of toolkits that we supply. We are backed by Battery Ventures, which is a software investment company, and that has enabled us to invest more in the technology that we license out to people, and it has enabled us to buy and acquire technology that fits with our portfolio of products, and that's part of what we're going to be showing you today. So I just want to explain a little bit about how we work and what's going on when we go out into the field. So we believe in fueling innovation with unmatched 3D technology. What do we mean by that? Well, when I go to a show and I see a stand with a company on it, and I look at it and I think, oh golly, they've got our software and they're using our software to create their end user application. I'm seeing it more and more now. Closer to home, I was at a football match in Sheffield, at Sheffield Wednesday, and on those electronic hoardings that go along the bottom, there was ANSYS, who are a user of CAE technology. So it was really nice to see that in a home environment. I want to just quickly run through our technology, our SDKs, and just show you the workflow. I'm not going to dip into the stuff we're covering today, but what I want to talk about is if you're creating a piece of engineering software, generally you're going to need to read in data to get yourself started. So we do have a very comprehensive CAD reader called Hoops Exchange. Andreas is going to go into detail about that later. We have AE importers as well that support the major other CAE solutions out there. And we've been growing into AEC by adding formats like IFC and Revit. The visualization part of this, the graphics, it's something we've been doing. We're experts in the Hoops products cover that. We've got Hoops Visualizer and Hoops Communicator that work on both desktop and in a browser, and they provide real-time manipulation of large 3D models, very useful for when you're creating an engineering piece of software. We've also got some CAE software, which is going to be showing you how we do CAE visualization. I'll not dwell too much on that. On the solid modeling front, we've partnered with the best in class. So we've partnered with Siemens for solid modeling solution. Their Parasolid solution is used in more engineering applications than any other solid modeler, which is why we partnered with them. We also have a mesh modeling system from MachineWorks, which we're going to be covering here as well. And that's a great way of preparing your data for rapid prototyping. It's a great way of taking your scan data from the scan and creating a mesh from that. And we're also going to be seeing how we can use that in a CAE workflow. Also on that list are CAD engines, and they do include modelers, but they're a full CAD environment. So if you want to create a specialist design solution for designing whatever, rather than inventing your own CAD engine, which is an enormous task, you can take the world-class Autodesk CAD engines and build your own solution using AutoCAD OEM or Inventor OEM. In the simulation area, we have a great meshing tool. I'm going to let Andres explain that, and the solver as well. Downstream, what we see is that companies that produce software need a way for the non-technical people to view and consume that data. So we support a way to output to HTML. We can use QR codes. We have 3D PDF output, and we also have the standard CAD outputs as well from our Hoops Exchange workflow. So I'm going to just give you a quick overview. These are our CAE partners that we have today, and we're covering all of the major providers of CAE solvers and technology out there, but we're also supplying a lot of enterprise accounts like BASF and SAP with the tools they need to use internally. So I'm going to quit there, and I'm going to hand you over to Andres.
Thank you, David. Let me get my screen up and running, and we'll kick things off. So, yeah, my name is Andres Rodriguez Villa, if you say it in Spanish, as I am Spanish. I'm product manager for TechSoft 3D CEETRON software toolkits, which have a main focus on simulation and analysis development, very much around the finite element modeling. But before I start, we are going to give a couple polls during this webinar. So this is the first poll time. Jen is bringing that poll up, and a quick question is really to understand where you stand with respect to CAE. I'd like to know if you generate CAE results, basically if you produce a solver or not, or if your application feeds on these results. Give you a few seconds to figure that out.
Tell you the results are still coming in, so.
Oh, wow, people are puzzled.
Yes, yes. All right, we'll just call it there. Well, all right, thanks everyone, still going on that, I appreciate it.
Okay.
And I'll share the results real quick, just so people are interested in who's on the call.
Yep. Okay. Wow. A lot of people doing neither, so that's quite fun. Thanks for being here. Okay, so I'll move on now. And let's get back to CAE Toolkits. This presentation is really about showcasing the result of TechSoft 3D's acquisition strategy. As David said, in 2020, two companies were acquired, CEETRON and Visual Kinematics, and TechSoft is now in a unique position, basically, to provide dedicated technology at all stages of the CAE workflow. And if we have a look at this workflow, well, it has three distinct stages, as you all know: setting up the simulation data. This is also called pre-processing the simulation itself. That's where the compute takes place. And finally, when the results are there, the analysis and sharing of that data, which is also known as post-processing. And so building an application that supports this workflow involves a wide variety of skills and technologies, and we think that some of these are not necessary to be reinvented. So I'm going to run you through what we can suggest for these technologies. And let's have a first look at importing the geometry. Yeah, some CAE applications are actually happy to propose an interface to standard formats, such as good old STL or IGS, or maybe even STEP. With Hoops Exchange, it's quite straightforward to expand that input to 30+ standard formats, as you can see on this slide, and hence offering a direct interface to the design models. Hoops Exchange reads this data, and what's interesting for us, Hoops Exchange can get all the data in the CAD files, but what's interesting here in the CAE process is really getting a tessellation out of those files. It could be the tessellation that is in the file, but Hoops Exchange also generates tessellations that will be used as input to the CAE meshing process. So now we have a geometry, it's been imported, it's not a mesh, and we need to start preparing it for meshing. We all know that CAD tessellations and meshing don't always mix well. Meshing requires non-manifold, watertight tessellations with no folds or overlaps or any geometric failure. And more often than not, a healing stage is required to repair the tessellation to get it ready for meshing. At this stage, as David said earlier, TechSoft 3D is the exclusive reseller of Polygonica, which is a toolkit developed by MachineWorks. And beyond repairing tessellation messes, most of the time automatically, Polygonica also provides other functionality that's quite relevant to the CAE space. I can talk about Boolean operations, defeaturing, and mesh offsetting. Okay, so where are we? We now have a clean tessellation. It's ready for the meshing process. The clean tessellation is already sort of an initial mesh in itself. And it's going to be input to the mesh generation. And the purpose of mesh generation is really to produce a mesh that is well suited to the intended simulation. And here we have a new product called CEETRON Mesh, which is a robust all-purpose mesh generation toolkit for planar, surface, and volume meshes. It relies on exact arithmetic predicates and a consistent boundary recovery to ensure fail-free operation. It's really the main feature here. It's a robust all-purpose toolkit. Planar and surface mesh generators will provide triangle and quad dominant meshes. And the volume generator generates tet meshes and also has the option of producing pyramids whenever the surface elements are quads connected to the surface mesh. There are obviously various mesh size control options, both working in isotropic and non-isotropic mesh sizes. And finally, CEETRON Mesh includes bridges to Parasolid, ACES, and Open Cascade. And obviously, in the next month, we'll be finalizing an interface to Hoops Exchange, which will allow to connect CEETRON Mesh to the 30+ CAD formats we just saw, supported by Hoops Exchange. Okay, so this sort of ends the pre-processing stage. We're going to be adding other input data, material parameters, boundary conditions, initial conditions, and throw that to the solver to get on with the simulation itself. And here, CEETRON Solve can be helpful. I mean, whether your core activity is developing a finite element solver or using a solver's result as input, that was sort of the question of the poll. You can think of an optimization application who's going to rely on FEA results or anything in the PLM space, and other situations where results are sort of the input. Whether you're doing one or the other, CEETRON Solve can help you boost both your development time and the time that your solver spends solving, the CPU time, basically. So the first component or the first side of the toolkit is a consistent framework to define models at the element level. This is where the governing equations are written and where materials and physics come into play. We provide an extensive set of elements, mainly focused on FEA. This includes beams, shells, solids, springs, trusses, etc. And we also have a nice library of linear and non-linear material models. So with all these blocks, you can put them together and actually build an FEA application or a thermal analysis solver. That's the first part. The second part, well, when all these local element matrices and vectors are assembled, well, get a big system. This assembly is done by the second component of CEETRON solve, which provides all the linear algebra required to solve the linear systems or eigenvalue problems. All the algorithms are parallel on shared memory architectures. We do have distributed memory implementations on our roadmap. Won't be done this year, but it's high on our list. So what can developers do? They can solve sparse linear systems. They have a choice of a direct multifrontal solver or one of the two iterative solvers that are provided, a preconditioned GMRAS and a conjugate gradient method. For eigenvalue problems, we have a block Langsos solver, which is best to extract limited numbers of normal modes. We also have an AMLS method, which is better applied on larger numbers of modes, thousands of modes. And finally, for buckling, we suggest a subspace eigensolver. You can see some comparisons here with other solvers on the market. And well, when the solver's done, it's really time for mechanical engineers to start digging into those results and making some sense of them. And for this, they rely on specific tools to extract meaningful data from the large data sets that are produced. They also need efficient tools to share this data with all the stakeholders. This is really the post-processing stage. And if we're talking about sharing CAE data, I would like to invite you to treat yourself to a 3D model on your phone. If you can scan that QR code while I'm running through the slide. CEETRON ENVISION is a component fine-tuned for CAE data processing. It's really focused on meshes and results. It also provides visualization, of course. It comes packed with efficient tools to seamlessly extract data from the large data sets, which enable a better understanding. Here I'm talking about cutting planes, animations, ISO surfaces, ISO volume spots, all these investigation tools that are required to make sense of CAE data. The display models that are used here, when you do a cutting plane, you get a display model. They can be visualized both on desktop with an OpenGL renderer and also in a browser using a WebGL renderer. And hopefully you've been experimenting this with your phones. Although providing the main 3D view of CAE applications is really at the heart of CEETRON ENVISION, its set of Python modules are gaining popularity. All the data processing functionality is available for Python scripting, which really opens the door to highly efficient engineering workflows. For example, you can run a Python script after a solver is finished and generate a browser-based dashboard of the simulation. It's ready to consume by the end user, by the mechanical engineer. Sort of automated post-processing. So that's sort of the last step of the standard workflow. We set up the data, we fed it to the solver, and we saw we can dig into the results. There are other technologies that are supporting this workflow all along. I just mentioned visualization and automation. Another useful functionality is really to support reading and writing of different CAE formats and to be able to interoperate with other solvers. A fatigue solver may need data from an external FEA solver. A material forming application may wish to export its results for further simulation, structural analysis, for example. Other examples include SPDM frameworks, generative design software, who really need to access data from various standard solvers. CEETRON Access enables this on a wide variety of formats, which are summarized on the screen. All of these formats can be read, and those in blue can be exported. I'm pretty sure that you'll agree that the main point of such a toolkit is actually to remove the pain of developing and maintaining these in-house readers and writers. We can take care of that, basically. That's what I'm trying to say. So that really wraps up a very high-level overview of how TechSoft 3D now supports CAE in many ways. And well, before I start a demo video, it's poll time again. CAE is a very general acronym. I'm really interested in gaining some insight on what type of simulations you are interested in. So next question.
All right, we've got a lot of participation coming in. Give it another 10 seconds. All right, gonna end the poll.
Yep.
Appreciate we had a strawberry in there. Thank you, guys.
No chocolate. Okay. Thank you. Okay, thanks again for those answers. Now let's go for this demo. Our consulting engineer Toshi in Japan took a few days to create this browser-based application to showcase what I just presented, the full coverage of the workflow. We'll be importing a brackets design, adapting the geometry for the simulation needs with Parasolid. Actually, I didn't talk about Parasolid, but David did earlier on. We're going to edit the geometry, then we will mesh it and perform a static analysis to determine which of fillet welding or groove welding is the best way to manufacture the part. So I'm going to run the video. And let's dive in. So the first step is to load the model's geometry. Here we will open a step file in this dialog box on the client side. It's a browser-based application. On the server side, Hoops Exchange is reading the CAD data and sending back the display model to the Hoops communicator screen for rendering in the browser. In the backend, we started a Parasolid session as we're going to be editing this geometry. Right now, we're going to use the feature detection of Parasolid to remove details that are not relevant, such as that hole. Next, we'll extract weld lines and add weld geometry, detecting the relevant edges and adding a chamfer to create the fillet weld beads. We now select and offset the upper circles of the holes where bolts will fix the bracket. And these faces will be used to specify a fixed constraint boundary condition. In the same way, we temporarily create the mating rubber block that we'll be pushing on the bracket. We can then imprint that on the vertical plate to identify the area that will be loaded. This is very simple using Parasolid. And once we have that rectangle, well, we can get rid of the block. The three plates in this product are not actually attached to each other, but are connected by fillet weld, as you saw. And we'll be modeling this by introducing a small gap in between the plates using temporary thin sheets and subtracting them from the geometry. Okay, so with these edits, we now have a geometric model of the manufactured part. We can move to the FEA space. We're going to change the screen. After we run the mesh, this is CEETRON mesh being run with a constant mesh size. Surface mesh is generated, then the volume mesh almost immediately. You will notice the good quality of the elements, close to being equilateral. The mesh size is chosen to produce 3 elements across the thickness. So we are now truly in the CAE space. CEETRON ENVISION is being used to show the mesh. Here we're back on the Hoops communicator screen and back to the CEETRON ENVISION screen. Moving from one to another is very simple. As I mentioned earlier, CEETRON ENVISION also allows to analyze the model. Here, you can add a cutting plane to look at the internal mesh, and you can easily move the plane along the part to inspect the internal mesh. You can get rid of the plane and move on now. Next, we're going to set the boundary conditions. We go back to the design space in Hoops communicator. We select the relevant surfaces. And we'll apply a fixed constraint on these elements, which is quite simple because CEETRON mesh and Parasolid know about each other. It's this interface I was talking about. Next, we select the rectangle, apply a 3,000 Newton force in the X direction, select the material, and all the data is there. You can run the solver. It's going to take a few seconds, and we'll be able to take a look at the results. There you go. We're interested in the level of stress in the part, so we take a look at the von Mises stress. Focusing on the areas where it's high, we notice that most of the part displays low stress levels, the blue areas. By activating transparency, we see a high stress concentration inside the part, maximum of 65 MPa. And this is due to the fact that the weld bead is actually only on one side of the weld, which is actually a bad design choice if you want to avoid stress concentration. So we go back to the design screen, and we're going to model the weld that joins the two plates as a groove weld. And in this case, the plates will be fully connected, so we get rid of the gap we created previously by using Parasolid's undo to remove the thin plate artifact, and then the union Boolean operator to join the plates. The other welds remain as fillet welds, so we'll keep the gap, and we can regenerate the mesh and move back to the simulation screen, just powered by ENVISION. No change in the boundary conditions, so there's nothing to do at this stage. And we can just run the solver again to see if our design change is beneficial. Take a look at the results, and this time the stresses are relatively uniform. Levels have decreased considerably. We have a max of 27 MPa. And it so happens that this value fits the mechanical requirements of the part. And well, we did our job. We found a valid manufacturing option. Finally, we can play a mode shape animation of the deformation just to check on the dynamics of what's happening to the bracket. This is really a built-in feature of CEETRON ENVISION, requires only a couple lines of code. While the animation is running, we can get a better understanding of the internal stress distribution by adding a cut plane. We can move it around, change its orientation, all this dynamically. Each of these requests is actually handled by the server side. So every time you move something, it goes back to the server, and the server streams back an updated display model. We have some animation controls. The application uses CEETRON Access, so it's quite easy to export the results in an OP2 file and offer them to download to the end user. As the demo just showcased, CEETRON ENVISION is available for CAE web application development. And it also has a desktop edition. Our OP2 file is easily imported in ENVISION's demo analyzer for desktop, which offers exactly the same functionality as its browser-based buddy. This and other demo applications are available for download on techsoft3d.com. So that sort of ends the demo. I wanted to summarize. The demo has shown that a complete CAE workflow could be implemented in a browser-based application using TechSoft3D's toolkits at every stage. We loaded a CAD model, did some editing on it, generated a mesh, set the boundary conditions and material. Then we ran a simulation with a solver we developed, analyzed the results, and decided to change the design to obtain one that fits the requirements. So that sort of ends my presentation here. It's time to see the toolkits in action in real-life applications. And I'm happy to hand over the screen to Andrew Sartorelli, who's Product Manager of Integrations at CEETRON. You're up, Andrew.
Thanks, Andreas. Let me go ahead and share my screen. Hopefully everyone can see now my presentation.
Yep.
So it's a pleasure to get a chance to speak to you all today about what we're doing at CEETRON and how we're using CEETRON technology, as well as TechSoft technology, to accelerate our mission of creating connected engineering workflows. So as I said, my name is Andrew Sartorelli, and I'm the product manager here at CEETRON for integrations, as well as handling our partnerships. At CEETRON, we believe, along with many of our customers, that the way products are developed today will change in the coming years, and frankly needs to change. Oftentimes today, engineers are tasked to do the same task over and over again manually, whether it be sketching and designing CAD parts or running a structural analysis on a component of a car. With Synera, we want to change that. We are building a platform for connected engineering workflows that enables knowledge to be captured, reused, and replayed effortlessly by fellow engineers or designers, or in the future, even AI assistants. By bringing together disciplines and capturing knowledge, engineers of tomorrow, or for those using Synera today, are able to design the next generation of cars and airplanes faster than ever before. Engineers, designers, and analysts and scientists often work with environments that are less than ideal. Current design processes are linear and not yet adapted to agile workflows like software development is today. Not because engineers and designers don't want to work in these environments, but because the tools don't exist to enable them to work in this manner. Folks are tasked with doing the same work again and again, where there's no or very limited new knowledge added to the process. At customers, tool landscapes are very fragmented because they need to use tools from a variety of vendors and want to use tools from different vendors. And manual rework is ever present, even when we know there's a better path forward. The problems of tomorrow will necessitate a change in processes, whether it's the need to reach the market faster, producing more diverse and supply chain tolerant parts, or dealing with the changing demographics in the workforce and the need for creating more engaging work environments for employees. Most people don't actually want to spend their time doing the same work over and over again. They want something new and different to challenge themselves. We see these inefficiencies brought by having engineers and designers spend time on tasks which don't add value, costing companies upwards of $300 billion a year in lost efficiencies. At Synera, we bring forward a low-code environment for engineers to capture their knowledge in an intuitive manner. And like any good platform, we're open and engage with partnerships with a variety of companies to enable our users to connect nearly any tool they use in their process. And as soon as engineers have captured their knowledge, we allow them to replay it and reduce the manual steps they or their colleagues need to complete the same task in the future. Now, I believe we can only bring forward our vision of a connected engineering workflows through close partnerships. And TechSoft 3D and CEETRON, or formerly VKI, technologies are helping us in that regard. Instead of reinventing the wheel at Synera for having readers and writers for tools like ANSYS or MSc Nastran, we're able to use those libraries to do much of the heavy lifting for us, thanks to CEETRON and TechSoft 3D. And when it comes time to enable viewing those results from these analyses, of course, there was a library to enable us to do that in our viewport and easily display simulation results or CAD geometry. And when it came time to read in different CAD data from a variety of tools, whether it be Siemens NX, Autodesk Inventor, SolidWorks, or others, the Hoops Exchange library had a solution for us, easily enabling us to expand our supported CAD formats with limited changes needed for our code base. When I'm forming partnerships, it's a great enabler for me to know that we can easily connect to our partner tools and read almost any format that they're using. And as I said earlier, engineers can start building the processes of tomorrow with their knowledge today inside of Synera. For an example, at EDAG, for instance, we can see an automotive bracket where the design time to produce multiple iterations was reduced significantly, with a 70% reduction in process time, enabling the end user to design a more performant part in less time than with traditional design and engineering methodologies, simply by capturing and reusing their engineering knowledge. So now I want to jump into the software and give everyone an experience of what we've built here at Synera and how we're using some of the TechSoft and CEETRON technologies. So I'll start first with just a simple introduction to what is low-code environment and what is visual programming, because it may be new to some folks watching today. So here we have a simple example where I've just simply drag and dropped some blocks, or I can even type here and say I want to create a slider. And I'm going to connect this to one of my inputs. In this case, we'll do a multiplication. So I could say, I want this value to range from 0 to, let's say, 10. These two numbers from the two sliders, item A and item B, get multiplied together and go into this final node here to generate a sphere. But we can simply drag one of these sliders and see the geometry is changing. In this case, we're using PowerSolid to generate a sphere here, thanks to our relationship with TechSoft 3D. but we can get into a bit more complex workflows than just generating a sphere with Sonera. So I'm going to jump over to a workflow I already have prepared here, where we step through the creation of an automotive control arm for a Formula E car. In this case, Sonera is used to capture the entire process from start to finish. We start with the technical specification, or maybe we're importing some data in CAD format, or below, maybe reading in some information from Excel that contains our material information that we're going to use downstream in optimization and simulation. And of course, on the right-hand side, we have our viewport to always have a view of what's going on in our low-code environment so that we can visualize what we're programmatically doing, which is always handy when we're troubleshooting, building workflows, and capturing this knowledge to start with. So in this case, I'm reusing a workflow that another engineer created for me, and they've happened to document different steps and the expected results for those. So I can easily see here, this is the expected result as I start my process. So I'm not going to step through every detail here, but we'll step through the entire process and get an understanding of how this workflow works and how we're taking advantage of some of these great partner technologies. So after we go through and read in some of our geometry data, we go through and start creating a parametric design space for our optimization problem, so that we can move some of these positions of different bolt holes and other attributes of our part throughout the process to really optimize the part. We'll see at various stages, we have some design parameters called out by the engineer that we may want to play with. In this case, I'm going to hold off on making some adjustments here so we don't trigger all of the downstream simulations to recalculate. But we can see we have a lot of variety of options here that are easily accessible, while the main workflow has been constructed by the engineer. So after going through and designing the design space, we go ahead and start generating the part. And this is again where we're using some of these CAD operations to generate solid geometry. So we'll go through all the way down towards the end, and we can see entirely within Sonera, we've generated this part that we're going to use to start generating some of the loads and boundary conditions for our analysis. And the next stage, we start generating RBE elements, thanks to some of the CEETRON libraries that we have access to. We also generate some FE boundary conditions through various states in the workflow here. And again, we won't step through all the details, but at a high level, we can see that we've actually captured the engineer's intent in their process here through documentation, as well as the visual programming environment. Finally, we can take the next step of doing a generative design. In this case, we've partnered with Hexagon, with their Hexagon Amende product to do topology optimization. Again, tying in some of the loads and boundary conditions that we previously set up, we can run an analysis and end up with an optimized part. Again, here we can see the cached result from the engineer, letting us know what we can expect if we were to start to change some of the variables on the inputs. But of course, we know that we don't just want to optimize this part. We want to make sure it holds up in the end to regular analysis. So the next step, we're going to take this mesh geometry and we're actually going to reconstruct it back into CAD geometry. So we generate a mesh, we generate a boundary representation, and then thanks to Parasolid, we do a few Boolean operations and we end up back with those prismatic surfaces that we need to bring this back into our CAD tool. And now we get to the state of actually analyzing our part. And again, here we have the option, thanks to TechSoft 3D and CEETRON, to either analyze this with a built-in simulation solver, or we can actually export this out to a tool like ANSYS, Nastran, Abacus, because we have access to all of those libraries and connections. And then the final step, we can, of course, take a look, doing a few simple calculations through the visual programming environment to figure out the structural performance of the part, maybe the stiffness. Maybe we want to compare the weight from before and after, or even do some costing analysis thanks to our partners at Fraunhofer IAPT to manufacture this part with laser powder bed fusion. We can see here some of the nodes and inputs going into this process to help determine that costing analysis. So I want to thank everyone for giving me a chance to show you a bit of what we can do at Sonera. And at this point, I want to pass it off to my good friend John Wild at SimScale to talk a bit about how his company is using TechSoft 3D and CEETRON.
Cool, thank you, Andrew. You have to also somehow answer one of the questions that came up. I also don't know the answer to it, why you changed the name of your company. I guess Lotus caught up with you and wanted their car name back, but I don't know. Is there a reason?
So we decided to go forward with a new name for the company, and I think better represents our vision. And yeah, didn't want to have the comparison to the car.
Cool. Thanks, Andrew. Appreciate it. Okay, so I'm going to take something like 10, 12 minutes just to give you a little bit of a run through on our company and how we work with TechSoft. So I'll talk a bit about us, how TechSoft supports our platform, and then I'll jump into a live demonstration to show you how we're leveraging the TechSoft tools inside SimScale. So SimScale's been around for something like 10 years. We have about 125 employees, and our goal is really just to help all engineers innovate faster by leveraging simulation. And we have a tool that's been built from the ground up natively in the cloud. So it's only browser based. There's no installs, nothing, no licensing, nothing of that kind of complexity. You can always get immediate access. I'll walk through like a few of our tenets. So one of them is, like I said, we're cloud native. So there's no VPN, no remote desktop. You just have a simple login, much like with social media, although I suspect we're a bit more trustworthy with your data. We have one platform with loads of different physics available. On the right-hand side, you can see the CEETRON post-processor. This is actually a motor. It's shaded by temperature. So the red parts are hot, the blue parts are cold, and you can see fluid going through it. So that's like a CFD analysis. And then in the bottom right, there's some structural stuff too. And our users experience the same kind of workflow, whatever type of simulation, whatever type of physics they want to work through. So we can do lots of different things all on one platform. Again, being on the cloud, our users can collaborate. So we have lots of customers with many, many engineers all working with SimScale simultaneously. And if they want to, they can jump into each other's projects, ask each other questions and support each other. If they need more help, they can reach out to us directly. So there's an option to share your project with support, and you can get live chat in the moment that you need it. So we have a host of engineers here, and we have something like a 30-second response time. And if you want us to, we can jump into your project and help you in the moment that you need it. Everything runs at scale. So a lot of the desktop tools run one simulation at a time, or maybe you can batch them in series, which can take a long time. We don't do it that way, so we run everything in parallel always. So you could run one simulation like this motor, or you could run 100 different motors in the same time it would take to calculate one. And then you could compare them all side by side and very quickly decide which your optimum design was. And we're also cost effective. So all of that kind of wraps up into a product that everyone can afford access to. And we have users from, or companies from that have maybe one engineer up to hundreds of engineers, all leveraging SimScale in totally different ways. And we've been working with TechSoft for a long time now, and we leverage 3 of their tools primarily. I'll explain how. So we work with all of the major CAD manufacturers or CAD providers, and we import their CAD into SimScale so that we can then do simulations. Obviously, they update their CAD, they update the packages, and it's difficult to keep up. But through working with Hoops Exchange, we don't have to worry about any of that. We're basically always up to date. So all of our users, if they update their software, they know that they can immediately work with SimScale, which is amazing. CAD isn't always ready for simulation. It sometimes depends on what you use and how you leverage SimScale, but sometimes it needs to be clean, and we can leverage POLYGONICA to help get CAD ready from the version that's uploaded to a clean version that we can work with. And then we do our post-processing with CEETRON. So again, you can see it on the right-hand side here, and I'll demonstrate it shortly as well. So this enables us to pull raw simulation data from all of the different solvers that we have, and our users experience the same post-processor. So whatever solver they've come from, they always post-process in the same way, so they just need to learn one thing. And then we can generate visualizations like you can see and explore simulation results, start to ask questions about the assemblies and whatever we're manufacturing to make it better. And now I'll jump into a quick live demo. So this is SimScale. It's running in the browser. It's live. And this is a globe valve. So we have flow coming in here on the left and exiting over here on the right-hand side. I have a cut plane passing through the middle, and that's showing velocity. And the red areas are high. There's a legend at the bottom. The red areas are high, the blue areas are low. So you can get an idea that as the flow passes through the small gaps, it has to speed up. And what we want to do is to try and make sure that there's not too much recirculation, so that we're not taking too much energy away from the fluid as it passes through. This is actually gasoline. So there's a few things we want to do that. We could look at an iso volume. So this basically helps us understand that the flow goes to two sides, and it definitely goes more to the right than the left. So already we have some kind of imbalance, and we're not leveraging the whole area that we have here super well. And we can dig into that even more. Back to my plane, I can look at vectors. And you can see on the top two sides of the valve, we've got a lot of recirculation, and this isn't ideal. So we're just wasting energy here, and we're taking energy out of the system for no reason. And ideally, we want to try and avoid that. And again, still leveraging the post-processor we have here, we can dig more into the data, and we can look at some traces. So this is basically throwing in some traces from the left-hand side here, and they pass through the model, and you can see where they go. And the idea is to understand, do they pass through? Do they recirculate? If they recirculate, where does that happen? And we can animate it too. So I think this is using what you showed before, right, Andre? Just with our overlay on top of it. So this is the same post-processor, but using our technology on top. And we can basically now see that the flow passes through, the bulk of it goes through nicely, but lots of it kind of recirculates. And that's what we want to try and design out of the assembly. And how we got to there, you can set the model up on the left-hand side. So this was the original model, the original valve that we had to work with. And we just extracted the fluid volume to do the simulation with. But as I said at the beginning, we can do lots of different simulations inside SimScale all at the same time. And this is a structural simulation as well in the same project. And what I have here on the internal surface that you can see is blue as an internal pressure. So we're kind of blowing up the valve as the gasoline flows through it. And what we want to do is understand, will it deform, and if it deforms, will it deform permanently? And we can, again, run the simulation, and we can post-process the results to try and understand that. And the view that I set up highlights basically where the stress is highest. So a similar thing to before, looking at flow, but this time we're looking at stress inside solids. And you can see the red areas highlighted. And that's basically helping us understand that these areas deform. And because the stress is above a certain value, they could deform permanently. Okay, that's a super quick overview of SimScale, TechSoft, and how we work together. And now I'd like to hand back and answer any questions you might have.
Thanks, John. That's fabulous. I'm just going to share my screen. So yes, anybody who has got questions, we can answer them now. You put them in chat, and we will go through them. So I think Andres may be able to help.
Yeah, sure. Jen, do you want to read out the questions that you selected?
Maybe
No.
she's mute.
Maybe she left. Okay, I'll take him. Sorry.
No, it's okay. I had, mute first time on a Zoom call or Zoom, first time.
Okay.
Real quick, also, David, I think you had one more slide just so that we can tell people how to reach out to us if they want.
Yeah, sure. I was
that
just
slide
gonna...
up, that'd be great.
Yeah, so we're going to be running an event for CEETRON ENVISION. You're welcome to join that March 1st. You can go to texoff3d.com to register and learn more about our tools. If you'd like to reach out to Andres, our product manager on CAE Tools directly, you've got his email address there as well.
Or you can hit that QR code. It's kind of fun. All right, so we've got quite a few questions coming in, and so I'll just go through these as they're going. Let's see. The CEETRON ENVISION web-based does the rendering. Does it do rendering in the browser? How does this affect performance?
Depends on what performance, if it's the rendering performance or the the fact of streaming. If it is the fact of streaming, for your everyday models, it's really a sort of an instant process. You'll hardly see it stream in, and at the end of the day, you get a desktop-like user experience because we are using client-side rendering. There are extra large models, and here I'm talking about 30, 40, 50 million elements, really depends on the shape of the model. There you will see the streaming going on, but the good thing is that it is progressive streaming, so you can immediately start interacting with the part, even if the streaming isn't finished yet. You can go on cloud.ceetron.com. We have a gallery there and with different sizes and different types of models, which will give you an idea. That's hosted in the Netherlands, I think.
Great. We've got some questions around the meshes as well. So can linear and quadratic meshes, love the words.
Yeah, all mesh generators in CEETRON mesh can provide second order or third order cubic elements as well. Yeah, that's built in.
Awesome. What about voxel messages? We had some questions about that.
Nope, that's really out of scope. The volume meshing is, as I said, TET generation and also hybrid TET pyramids to hook onto quads on the surface if needed.
Perfect. So I'm looking through here. Does CEETRON mesh support beams, one-to-many, and many-to-many mesh? Also, does it support contact definition?
Well, could you repeat, please? No, CEETRON mesh is really about, it's really about mesh generation. I don't think we have 1D elements there. It's really about 2D and 3D meshes. And contact would be handled by the boundary conditions and the solver itself. You'd have to define sets and stuff like that. But it's not in the mesher. The mesher is about really generating the mesh.
Great. Can I download .vtu data to the browser to visualize? Yeah,
I saw a couple of those people asking if I could upload actually the data into the browser and use it as a desktop application. It's a bit weird. Purpose being to have the data remotely and be able to stream it into the browser, but you could do that. The thing is, any ENVISION web application will have a server and will have a client side. I guess if you have both the server and the client on the same computer, it sort of looks like a desktop application, and there you could immediately stream the data from your laptop into the browser. It's doable. It's just a bit awkward, I would think, but I'd have to understand the workflow. So just reach out to me and we can have a closer talk.
Great. We had a more general one. What type of companies is your product design platform targeting?
That was for Andrew when the question came up earlier.
Okay, perfect. Sorry.
Perfect. So yeah, CEETRON is really targeting anyone with complex engineering workflows where you have repetitive tasks. So if you're working in the automotive space, aerospace, consumer goods, right, where you're creating a lot of the same work over and over again, I think you're a perfect candidate for using CEETRON.
Great. And then we had another one from someone. CEETRON Cloud is great, but it's limited storage. Is there another way to expand the storage or link to other cloud-based storage, e.g. OneDrive? Andres, did you catch that one?
Sorry? Oh, I'm sorry, I was answering someone else here on.
Okay, we're gonna go with the live ones here, buddy.
I'm running in parallel on shared
And
menu.
we're not gonna run parallel.
He's multitasking, multi-threading.
Yeah.
Absolutely, and I can't do that in Field. Yeah, go ahead.
Yeah, there was one about CEETRON Cloud is great, but about the limited storage. And then is there a way to expand the storage or link to other cloud-based storage?
For an account on CEETRON Cloud, yes, there's a limit. It's a free service. We used to have a premium subscription possible there. Reach out, we can probably find something, but again, it's sort of a demo application. You'd be better off by installing that on premises, and then again we can discuss how to do that. There's a sort of a private version of the repository.
Great. And then another one we had, how much does a license cost? I'll let you take that.
What product?
I like the answer, it depends. Yeah.
Who's the question for?
It's just, I think it's just general for, oh, I think that was for SimScale.
Okay, then I can answer. So it's relatively affordable either way, and there's a free kind of entry, right? So anyone can sign up at simscale.com, and then you can start simulating for free publicly though. So only our customers get private simulations. So everything is public to begin with, but you have a whole host of simulations just to do for free, just to experiment to see if you like the tool and can get value from it. Thanks.
Great. And then one more from you for you guys was, what solver do you use?
We have a whole host of solvers. So originally SimScale was built on OpenFOAM and Calculix, now Codester, and then we have a voxel-based LBM solver, and we've just partnered with Cimerix, and we're going to release 1 or 2 more solvers over the next year or 2 as well. But loads of different solvers, which is why it's nice working with you guys, because we can pull all of that data in different ways and put it into the same place. It's pretty cool.
We love the plug. Thank you so much. And we just got time for probably one more. If we don't get to it, then we'll reach out to you directly. What are the largest models supported by CEETRON and ENVISION in a browser-based application?
All the limit is the user's patience. Basically, there aren't built-in limits. What I usually say is that up to 30, 40, 50 million elements, and again, this really depends. It's the number of triangles that need to be rendered that needs to be looked at. But for your everyday models, as I said, it's pretty instantly. There's a theater model on cloudceetron.com that sort of showcases the limit. It has the 28 million elements. But again, it starts streaming, it's streaming progressively, and you get some interaction. We are going to be looking at server-side rendering. At some point, models do become too large for client-side rendering. Hoops Communicator already has this, so I think there's going to be an easy technology transfer there from one product to another in the coming months.
Fantastic. And we are right at the top of the hour. So
Amazing.
I am going to, we're going to close it up. We will send out a recording of this for anybody that's interested. And just thanks to everyone who's joined and answered questions and asked questions. And especially thanks to our partners, John and Andrew. We greatly appreciate it.